Good morning, students. Myself, Vijay Shankar from EC Department in Chevrolet Engineering College. Today, we are going to discuss about the summer properties in the set transformation. In the previous class and the last classes, the two classes, we discussed about the properties of the set transformation. Linearity property, shifting property, and shifting is also in the two ways, one-sided and the two-sided. And the third is a multiplication by n or the differentiation in the z domain. Now the fourth one, you can see here the fourth one is a multiplication by an exponential sequence a power n or the scaling in the domain, z domain. Multiplication by an exponential sequence an or the scaling in the z domain. So a power n x of n. Z transformation gives x of a inverse z, or it is a z by a. So suppose you can take the definition. X of z is equal to the sum of n is equal to minus infinite to infinite. X of n. What is the x of n? Now we are taking as a power n x of n. A power n x of n z power minus n. This is a definition of the z transformation. We substitute instead of x of n is a power x of n, a power n x of n. It is equal to sum of n is equal to minus infinite to infinite. X of n. Now I'm rewriting the whole power n as a inverse z whole power minus n. Now it is in the form of the z transformation for definition only. Instead of z, it is a inverse z. Instead of z, a inverse z. Therefore, it becomes of x of a inverse z. The z transformation of a power n x of n, or otherwise x of z by a. So the z transformation of a power n mu of n, not the mu of n, x of n, a power n x of n. The z transformation is x of z by a, x of z by a. The simple thing. You can take this as a power n and z power minus n as a inverse z whole power minus n. Minus into minus is a plus, it becomes of a power n and z power minus n. Instead of z in the definition of the z transformation, having the inverse z is there. The scaling in the z domain. How much it is a scale? The 1 by a is a scale. Whenever there is a power n is multiplied for the signal, time domain signal x of n. Students. Coming to the next property, the time reversal property, the fifth one. Time reversal property. The time is reversed. The x of n, the transformation is x of z. Now the x of minus n, the z transformation is z inverse. You also can take the z transformation of x of n is equal to the sum of n is equal to minus infinite to infinite x of n z power minus n. Is it right, my students? Now instead of x of n, I'm taking the x of minus n. X of minus n, the sum of n is equal to minus infinite to infinite x of minus n z power minus n. I'm taking only the signal. I'm not replacing n with the minus n. Okay. Or if suppose if you think that it is a n is replaced by the minus n, what it happens here? The minus z power minus n becomes of so replace n is equal to minus n means z power minus of n is now the minus n. Okay, my friends. Minus n. Now we can rewrite this function as the sum of n is equal to minus infinite to infinite, the x of minus n and z power minus 1 whole power minus n. So what is the instead of z when I'm taking the signal is x of minus n, actually it is a x of z inverse, x of z inverse. Otherwise, you can take the transformation of the x of n minus 1, x of minus n is equal to the sum of n is equal to minus infinite to infinite. Take the signal is x of minus n in the definition of the z transformation, z power minus n. Now, let's assume minus n is equal to p or m, whatever it is. Minus n is equal to p. That is equal to sum of now what is the value of n is equal to minus infinite? We are changing the values of n in terms of the p. Minus infinite becomes a plus infinite and plus infinite becomes a minus infinite, and x of minus n now becomes of the p, and z power minus n value is the minus p. Okay, minus n is nothing but the p. That is equal to, either you can add from minus infinite to infinite or infinite to infinite, is both are the same. So I'm changing the limitations as p is equal to minus infinite to infinite, x of p, and write this expression as z power minus 1 whole power minus p. So according to the definition, the n value is a variable, but here the p is a variable. Nothing is a change. But what is the z here? Z inverse. And I'm taking the x of minus n. What is the z transformation? The transformation is x of z inverse. The pair of x of n is x of z. Now the pair of x of minus n is a x of z inverse. Nothing but it is a time reversal, or is a folded function. X of minus n is a folded function of the x of n. X of n z transformation is x of z. X of minus n z transformation is a x of 1 by z, or x of z inverse. Okay. In the sixth property, conjugation property. Sixth property is conjugation property. If the transformation of x of n is x of z, the transformation of x conjugate of n is a x conjugate of z conjugate. X conjugate of z conjugate, we can call it as x star of z star. So take the definition of z transformation. The transformation of x of n is equal to, what is the definition? N is equal to minus infinite to infinite. X of n, z power minus n. Okay. Now I am taking this x of n as a transformation of the conjugate of x of n. The conjugate of n. I'll substitute in the definition of the transformation. Sum of n is equal to minus infinite to infinite. X star of n, or x conjugate of n, z power minus n. Okay. Now I'm taking the whole, the term is star here. The total term is a star. It becomes of sum of n is equal to minus infinite to infinite. The conjugate and conjugate, nothing but it is a, we will get the real. So I'm taking here it is x of n. So when it is multiple power having the x star, and in the z also I'm taking the z star. So conjugate of conjugate, we will get the real here. Z star of minus n. Now it is in the form of the definition of the z transformation. Instead of z, here the z star, or z is conjugate. So x is z star, x of z star here, and already we have the whole star. It becomes of x star of x conjugate of z conjugate. Got it? So conjugation property saying that the input is conjugate, not the input here, the time domain is conjugate, and the z domain is conjugate, and also the z is also the conjugate, x conjugate of z conjugate. Take the definition and substitute here the x star of n, z power minus n, take whole star here, x of n, z star of minus n. According to the definition of the z transformation, it is in the x of z, but instead of z, there is x z star, whole star. You can derive this function as a x star of z star. Got it, my dear students? See, convolution property. After the conjugate property, there is another property is the convolution property. So x1 of n, this is a transformation is x1 of z, x2 of n, this is a transformation is x2 of z, and the x1 of n, the convolution of x2 of n, this is a transformation is time is convolution, the frequency is multiplication. We already know the Fourier transformation. We already seen. We already discussed about the Fourier transformation, Laplace transformation, and also the Fourier series also. Taking the convolution in the time domain means the frequency is a product, and the frequency is the convolution means the product is in the time domain. Now we're taking the definition of the transformation. The transformation is the sum of n is equal to minus infinite to infinite x of n z power minus n. What is this x of n? See, if I'm taking the transformation definition, the x of z is equal to, listen carefully my dear students here, the sum of n is equal to minus infinite to infinite x of n z power minus n. So what is the x of n? We are taking the convolution. What is the convolution of the two sequence? The sum of n is equal to minus infinite to infinite. X of n is x1 of n with the convolution of x2 of n z power minus n. Got it? So what is the formula for the convolution in the discrete time function? This is a summation. The sum of n is equal to minus infinite to infinite. Sum of n is equal to minus infinite to infinite. X of 1 with the convolution of x2 of n is again the summation. The sum of k is equal to minus infinite to infinite x1 of k, x2 of n minus k. Is the definition according to the convolution of the two sequence, and z power minus n. Got it, my dear students? So now the n variables are all you can write it as one side, and the x variable, k variables you can write it as another side. And the first term is there, the sum of k equal to minus infinite to infinite, k equal to minus infinite to infinite, x1 of k, x1 of k, and the remaining function I'm writing here, the sum of n is equal to minus infinite to infinite x of x2 of n minus k z power minus n. Now in the second term you can observe here the x2 of n minus k, nothing but it is a shifting property. So according to the shifting property, z power minus n x2 of n minus k means the term z transformation is multiplied with the z power minus k. Z power minus k. Is it right, my dear students? Z power minus k. Or otherwise, you can directly taking it as x2 of n minus k. N minus k is a p. Substitute that, or otherwise directly by using the one of the property, you can write it as a sum of k equal to minus infinite to infinite x1 of k Now I'm writing this as total function, this function as, by using the shifting property, saying that z power, because these are the positive values of k, n minus m, nothing but z power minus m, minus k, and it is multiplied with the unshifted z transformation, x of z. And what is the signal here? The x2. So I'm writing it as x2 of z. Got it? And now here observe this one, sum of k equal to minus infinite, x1 of k z power minus k. The k is a variable here instead of n. It is also one of the definition of the z transformation. It is x1 of z, since the signal is x1, multiplying with the x2 of z. Got it? The convolution of the time domain signals, x1 of n with the convolution of x2 of n, the z transformation will get the product of the two signals, x1 of z with x2 of z. Got it, my dear students? The same way, what we did in the Fourier transformation, Laplace transformation, and the Fourier series, there we are using the integral of integral minus infinite to infinite, x1 of tau and x2 of t minus tau dt. The integral value, since it is a continuous time function. Here, the discrete time function, we use sum of k equal to minus infinite to infinite, x1 of k, x2 of n minus k, you can substitute here. Otherwise, without using the directly by using the property, you don't know that one, you can directly take the n minus k is equal to p, n is equal to p plus k, and n is equal to minus infinite, p is equal to minus infinite, n is equal to infinite, p is equal to infinite. And substitute here, p is equal to minus infinite to infinite, x2 of p is z power minus p plus k. And according to the definition of the z transformation, this total function in the parenthesis is x of z. Here the signal is x2, then it becomes of x2 of z. Okay. And sum of k equal to minus infinite to infinite, x1 of k z power minus k. These two signals are the definition of the z transformation with the signal x1 and with the signal x2, then it gets x1 of z and the x2 of z. Got it, my dear students? Next, multiplication property. Multiplication property. Multiplication in the time domain. But what we are saying here in the Fourier transformation and the Laplace transformation and the Fourier series, multiplication in time domain, there is a convolution in the frequency domain. But in the Z transformation, it is not the convolution in the Z domain, my dear students. Got it? This is somewhat a different property in the Z transformation. Listen carefully here. x1 of n is the x1 of z, x2 of z, the Z transformation is x2 of z. The product of the two signals x1 of n and x2 of n, the Z transformation, you have to prove 1 by the 2 pi j, the integral x1 of v, x2 of z by v, v inverse dv. Okay, you have to show that the product of the two time domain signals, the two discrete time signals, the Z transformation is in the x1 and x2 with the v as a variable and with a counter integral. Got it, my dear students? To prove this, first of all, you can take the Z transformation definition. X of z is equal to sum of n is equal to minus infinite to infinite, x of n z power minus n. X of n z power minus n. Now I am taking the another signal here. The x of n is equal to 1 by 2 pi j, the integral x of z, z power n minus 1 dz. This is inverse Z transformation formula actually. Inverse Z transformation. Okay. X of n as a signal here. X of n is a signal. It is a 1 by 2 pi j, the integral x1 of z, z power n minus 1 dz. And substitute this in the definition of the Z transformation for the one signal x1. The sum of n is equal to minus infinite to infinite 1 by 2 pi j, the integral x1 of v, x1 of v, and here it is a x of z. To prove the property, they are asking it in terms of v. So I'm changing this z as x1 of v, since I'm substituting for the x1 of n, v power, actually it is a z power, v power n minus 1, the dz, write as a dv here. And another signal is there, x2 of n, z power minus n. Got it, students? So take this 1 by 2 pi j, the integral x1 of v, it is a capital letter, my dear students, and the sum of n is equal to minus infinite infinite, x2 of n, z power minus n, and here the v power n minus 1 is v power n minus 1 and the dv. Okay, and write this v power minus 1 as a v, and take this as a v power minus n, z power minus n and the v power n. Take this is the denominator, z by v as a minus, take the common as a minus 1, minus n and v power minus 1. So sum of n is equal to minus infinite infinite, x2 of n, the z by v whole power minus n. Is the definition of the scaling property. According to the scaling property, scaling in z domain, that is 1 by a there. So you'll get x2 of z by a. Why it is x2? Because its signal is x2. x2 of z by v, v power minus 1 dv. Now it is in the form of 1 by 2 pi j, the integral x1 of v, x2 of z by v, v inverse dv. This is somewhat different property, my dear students. Multiplication property. x1 and x2, 1 by 2 pi j, the integral x1 of v, x2 of z by v, v inverse dv. Check this a transformation definition, and also the x of n as 1 by 2 pi j, the integral x of z, z power n minus 1, the dz. Using this formula of x of n, substitute in this and simplify simply to get 1 by 2 pi j, the integral x1 of v, x2 of z by v, v inverse dv. Got it, my dear students? And the next property, correlation property. Correlation property. Correlation means we know already correlation of the two types. One is cross correlation and another one is autocorrelation. Cross correlation means the two different signals. Autocorrelation means only the one signal, similar signal. Okay. Now what is the statement saying here? The correlation property is saying that x1 of n is a z transformation x1 of z, x2 of n, the z transformation is x2 of n. The correlation, cross correlation here, because it's a 1 and 2 is represented, r1 2 of n is equal to, not is equal to r1 2 of n. The z transformation is the product of the two z transformation, but one z transformation is a time reversal z transformation, x1 of z and x2 of z inverse. Z inverse means the signal is x of minus n. X of z will get the z transformation means the signal is x of n. We already discussed that one of the property, the time reversal property. Got it, my dear students? According to the definition of the cross correlation function for the discrete time signals, actually what is the signal here? X of n and the x2 of n is a shifted version of the n number of samples, x1 of t and x2 of t. The relation between both the signals is equal to 0. That is orthogonality. The 90 degrees difference is there. You can shift the signal with some samples and compare the two signals is identical. There is a correlation is between the two signals. We already discussed this correlation in the 4th unit, my dear students. Okay. So what is the definition? R1 2 of n according to the discrete time signal, it is a sum. Sum of L is equal to minus infinite to infinite. I'm taking the L. Simply it is a variable. because already we have taken it as a n. You take this as n here, or you can take the k also, or you can tau, x1 of tau, x2 of tau minus n. L is equal to minus infinite, x1 of L, x2 of L minus n, L minus n, and then apply the Z transformation of cross correlation function. The transformation of R12 of n is equal to, substitute this total function as x of n, sum of n is equal to minus infinite, sum of L is equal to minus infinite, x1 of L, x2 of L minus n, z power minus n. Simply I substitute the signal in this equation. Then rewrite L functions is one side and the n functions is the other side. Sum of L is equal to minus infinite, x1 of L, and sum of n is equal to minus infinite, x2 of L minus n, z power minus n. These are all the n terms is there. Here also you can use one of the property. We have that property saying that shifting property. Okay, shifting property. How many number of samples is shifted here? N number of samples. Otherwise, without knowing that, simply substitute L minus n, L minus m is equal to p, where n is equal to L minus p. N is equal to L minus p, where n is varies from minus infinite, the p is also varies from plus infinite to the minus infinite, because it is a value is when n is equal to minus infinite, the p is becomes of a minus value is there, so it becomes of plus. Even the summation, the minus infinite, or the plus infinite to the infinite, both are the same. Nothing is a difference. Now I can replace this as L minus n is a p. The sum of L is equal to minus infinite, x1 of L. Sum of p is equal to here the plus infinite to the minus infinite, x2 of p z power n. What is the n? L minus p. Minus of L minus p. Okay. And now change this as a minus infinite, plus infinite to minus infinite as a minus infinite to the plus infinite, x2 of p. And take the p value, the z power minus of minus p is a plus. So take this as z power minus 1 whole power minus p. Observe, this is one of the definition of the Z transformation with the signal of x2, and instead of z, there is a z inverse. Okay, write this as a z inverse here, x of z inverse. And what is the remaining function? The sum of L is equal to minus infinite. Here it is x1 of L and the z power minus L. Z power minus L. So L is a variable. It is also one definition of the Z transformation with the signal x1. So x1 of Z and x2 of Z inverse. Okay, convolution property saying. What it matters, students? The next property. So here the x1 of Z and x2 of Z inverse. Okay. See accumulation property. So no need of this one of the property, accumulation property. The sum of k equal to minus infinite to n, the x of k, and z by z minus 1 into x of z. So forget about this accumulation property. And now it's a very, very important, the one of the property we have, the Parseval's theorem. Parseval's theorem. So what is that Parseval's theorem? With the two signals, if I am taking the two signals, x1 of n and the x2 of n, x1 of n is a transformation is x1 of z, x2 of n, the z transformation is x2 of z. Okay. And you have to prove the sum of n is equal to minus infinite, x1 of n, with the conjugate of x2 of n is equal to 1 by 2 pi j, the integral of x1 of z, x2 star of 1 by Z star Z inverse dz. Here also you can use as a inverse Fourier the transformation formula. Inverse the transformation formula is there. The sum of n is equal to minus infinite to infinite, x1 of n and x2 star of n is equal to. I am substituting only for the x1 as the inverse the transformation. The sum of n is equal to minus infinite to infinite, 1 by 2 pi j integral x1 of z power n minus 1 the dz x2 star of n is there. Got it, my students? So rewrite the function 1 by 2 pi j the integral x1 of z, and in the remaining all the terms having the n is there. Write that n terms the sum of n is equal to minus infinite to infinite x2 star of n and z power minus 1 whole power minus n, and another term is there here because of z power n, z power n minus 1 you can write as a z power n z power minus 1. Okay, so that z power minus 1 is there here and the dz already taken, that is a z power n is here by multiplying the minus into minus. So observe here, this is one of the definition of the z transformation. Instead of z there is a z inverse, instead of z there is a z inverse, and also we can write these by conjugate property also. What is the conjugate property? Saying that you can write this whole star here, x2 star of n becomes of x2 of n, and z is becomes of z star. Okay, the two properties you can use here. So one is a time reversal property, as a z inverse we'll get, and the conjugate property, so it becomes of x2 star of z star inverse, or otherwise 1 by z inverse. You can write that this as 1 by 2 pi j the integral x1 of z and this x2 star conjugate and 1 by z star x2 star of 1 by z star z inverse dz. That is a Parseval's theorem when sum of n is equal to minus infinite to infinite x1 of n and the x2 star of n. The two signals, one signal is a real signal, is multiplied with the conjugate signal x2 of n by using the inverse Z transformation formula. 1 by 2 pi j the integral x1 of z z power n minus 1 the dz you get as 1 by 2 pi j the integral x1 of z and x2 star, this is x2 minus x2 star of 1 by z star z inverse dz. Okay, the Parseval's theorem and previous correlation. So the multiplication, you get the integral term. Multiplication property and the Parseval's property. There we'll get, even we are taking the discrete time functions, because we are using the inverse as a transformation formula to prove the Parseval's theorem and to prove the multiplication theorem. We'll get the integral. Got it, my students? And now, after these properties is completed, and we have the two theorems are there. Parseval's theorem is also the theorem, and these two, the initial value theorem and the final value theorem. Initial value theorem and the final value theorem. And these names we already heard in the Laplace transformation. These names we already heard in the Laplace transformation, my students. In the Laplace transformation also, initial value theorem and the final value theorem we have. So initial value theorem, it starts from the s tends to 0 and the s tends to infinite in the frequency domain. And final value theorem is in the time domain, it starts with the infinite and ends at the 0 and the frequency term. Now here also, initial value theorem, it starts when n is equal to 0 in the time domain, limit n tends to 0 x of n, that is equal to x of 0, that is equal to limit z tends to infinite x of z. Simple. Okay. But here, to prove this initial value theorem, only you can write as a definition of the Z transformation, but unilateral Z transformation, not the bilateral Z transformation, to prove the initial value theorem and the final value theorem. See, what is the initial value theorem? Statement is x of n, the Z transformation is x of z. When the x of n is a causal signal means right sided. The Z transformation of x of n is the sum of n is equal to 0 to infinite x of n z power minus n. Expand this function. N is equal to 0 means x of 0 z power 0 is a 1, so it is x of 0. When n is equal to 1, x of 1 z power minus 1, and n is equal to 2, x of 2 z power minus 2. When n is equal to 3, x of 3 z power minus 3, and so on. Okay, x of 0 and the z power minus 1 means we can bring that in the denominator, x of 1 by the z, x of 2 by z square, x of 3 by z cube, and so on. What they are asking here, the limit n tends to 0, x of n, that is equal to x of 0, that limit n z tends to infinite x of z. So now I am taking here the left hand side, we have x of z. So apply the limit z tends to infinite x of z and substitute the infinite in this equation. X of 0, x of 1 by the infinite, x2 of by infinite. So I'm taking here. What is the x of z we got? X of z is equal to x of 0 plus x of 1 by z plus x of 2 by z square, and so on. Now, in the initial value theorem stating that is a limit z tends to infinite. Apply the limit z tends to infinite here. Z tends to infinite x of z is equal to, what is the z here? The infinite. Substitute in the right hand side also, x of 0 plus x of 1 by infinite plus x of 2 by infinite, and so on. So 1 by infinite nothing but is a 0, my dear students. 1 by infinite is a 0. Plus 0, and so on. X of 0. Now we got the x of 0 is equal to limit z tends to infinite x of z. What is the x of 0? You can write as in terms of n. Apply the limit n tends to 0 x of n. What is the one value we have? Limit n tends to 0 x of n is equal to x of 0, that is equal to limit z tends to infinite x of z. That is stating in the initial value theorem. N is equal to 0 to the z is equal to infinite. Same thing we did in the Laplace transformation also. What is the Laplace transformation? When the t is equal to 0, x of t is equal to x of 0, and the limit that is equal to s tends to infinite s into x of s. That s into x of s is x of s. So remember, this is t is equal to 0, x of infinite, n is equal to 0, z tends to infinite. Where s is representing in the Laplace, z is representing in the z transformation. Now coming to the final value theorem. The final value theorem also, seeing here, the final value theorem stating that x of n is a z transformation of x of z. When x of n is a causal signal means it's a right-sided dominant. It's a one-sided signal. One-sided means unilateral. What is the stating that limit n tends to infinite? Now, the previously n is equal to 0 as the initial, and finally it is a n tends to infinite x of n. X of infinite, the limit z tends to 1. Z tends to 1, z minus 1 x of z. Z tends, not the z tends to 1, z minus 1 x of z. Got it, my dear students? So to prove this final value theorem, we have to know the shifting property. The shifting property we did the two-sided Z transformation and the one-sided Z transformation also. Okay, my dear student, one-sided Z transformation also. The one-sided Z transformation is a one-sided only, and x of n plus m, x of n plus m, this is a transformation of x of n plus m plus m means it is a towards the right side. This is a transformation of x of n minus m means towards it is a left hand side. This is a left hand side and this one is a right hand side. The positive values of m and negative values of m is becomes of minus is a plus. What is the Z transformation for this as a unilateral, not the unilateral, bilateral? Simple, it is a Z power, get the positive values of negative values of m, it is a positive power of x, z. And Z transformation here, for positive values of m, the negative powers of z, x of z. So bilateral, nothing but the two-sided function. Got it, my dear students? One-sided means there is a one signal is added, one term is added for the z power m x of z. Okay, when term is added z power m x of z and z power minus m x of z. That is here I am taking the x of n plus 1. Yesterday I told that z of the z transformation of x of n plus 1 is equal to, the z transformation is already z transformation is there. Sorry, is equal to only. Here also the z transformation it is equal to only. And z power, what is the m here? M is a 1. 1 into x of z minus z into x of 0. Z into x of 0. Still it is increases. It is becomes of z square. And here the z square x of z and it goes on increasing this one. And these values are decreasing. The power is decreases. So what I am saying here, z square x of z minus z square x of 0 minus it is increases this one, is a decreases z power 1 x of 1 and so on like this. So use this function as n is equal to 1 only. Here x of n plus 1 is equal to z of x of z minus z into x of 0 because only the one function is there. What is students? Now on both sides, see here on both sides, taking here the minus z of x of z, the transformation of x of n, and z of x of z is already there, and a minus is there, the x of z. So we'll explain clearly the z transformation of x of n plus 1, the one-sided signal with the sample, one sample is shifted. The formula is a z of x of z and minus z of x of 0. So what I am doing here now is the transformation of x of n plus 1 minus x of z. I am subtracting in the left hand side x of z and z of x of z minus x of z minus z into x of 0. Why it is in the statement saying that x of z is multiplied with the z minus 1. So already the z is there. You can subtract the minus x of z. Taking the x of z is a common, you get the z minus 1. To prove the final value theorem, I am taking subtracting on both sides with x of z. So in the left hand side, I am rewriting that as z transformation of x of n plus 1. What is the x of z actually? You can write as z transformation of x of n is equal to x of z only. Okay. Otherwise, x of n is a pair of x of z. I'm writing this x of z as z transformation of x of n is equal to, take the common here, this x of z. X of z, you can take the common. What is the multiplication factor here? Z minus 1 minus z x of 0. Got it, my students? So now here the z transformation, here also the z transformation is there. Apply the z transformation, sum of n is equal to minus infinite to infinite. What is the signal here? X of n plus 1 z power minus 1. And for these also the z transformation is there. Sum of n is equal to minus infinite to infinite. X of n z power minus n. And write this is equal to z minus 1 x of z minus z into x of 0. Okay. See, in these two functions, sum is common and the z power minus 1 is also common. Take that is a single term. Sum of n is equal to minus infinite to infinite x of n plus 1 minus x of n as one signal z power minus n. What it matters students is equal to z minus 1 x of z minus z into x of 0. Okay. Now expand this function. Since it is not the minus infinite, because we are using it is a unilateral Laplace transformation, start from the 0. Here's one-sided only. Causal signal. Causal signal means right hand side. And this also from 0 on. So expand with the 0 here. So x of 0 plus 1 is a 1 minus x of n is a 0. Whole multiply with the z power minus n is a z power minus 0 as a first term plus second term x of n is a 1, 1 plus 1 is a 2, x of 2 minus x of 1 whole multiply with the z power minus 1 plus up to so on is equal to z minus 1 x of z and minus z into x of 0. What is minus z into x of 0? Z power 0. What is the value of z power 0 here? 1 only. X of 1 as a plus value, and here you will get the minus. X of n and the x of plus 1. So expand when it is a limit z tends to 1, as here in the right hand side, the limit z tends to 1 in this equation. Limit z tends to 1. Here also you can take the limit z tends to 1 in the left hand side. Z is a 1 and the z is 1 here. So anything 1 power, anything with the value is a 1 only. Anything power 1 is a 1 value only. And what is in the parenthesis here? 1 minus 0, 2 minus 1, and the next value is 3 minus 2. Because of 2 plus 1 is a 3, and 3 minus 2. Okay, and apply the limit on both sides. So here is equal to. Now I'm taking the limit z tends to 1. And here also the limit z tends to 1, the second function. Totally these are two functions. And for this function also you can apply the limit z tends to 1 for expansion function. The product z inverse, z power minus 2 and so on, all the values is a z. And here the x1 of x of 1 and the minus x of 1 cancel. Here we get the x of 2, and there the next term will get the x of 3 minus x of 2, z power minus 2, the value is there. So x of 2 is also get cancelled. So on all the terms in the left hand side except the x of 0, here, remaining all the terms is cancelled. What it matters, students? X of 0 the value, and in the right hand side also x of 0, that to minus is equal to, in the right hand side, limit z tends to 1, z minus 1 x of z. I'm not substituting the z1 value here. For the second term, summation term is there, we can substitute the z tends to 1, means it becomes of minus x of 0. Minus x of 0. What it matters? And this minus x of 0 and minus x of 0 is get cancelled. Okay, and so on. What is the last term here? Also x of infinite. All the terms is get cancelled, and there is a infinite term is there. Infinite term. When I'm substituting the n is equal to infinite plus 1 minus infinite term. Infinite plus 1 minus infinite means one, before that value is also get cancelled, x of infinite. So here the x of infinite will get, and this we can write as a limit n tends to infinite, x of n is equal to x of infinite, that is equal to limit z tends to 1, z minus 1 x of z. So only one thing you have to remember, you can use one-sided Z transformation shifting property with a sample of 1. Then on both sides you can subtract with x of z and write this function as in terms of the Z transformation definition and simplify. For it matters, friend. You see here x z into x of x z into x of z minus z into x of 0 you can check here. And see the minus z x of n, and already these are multiplied with the x of z with the z minus 1, and that is equal to the sum of n is equal to minus infinite x of n z power minus n is a Z transformation, and these also the sum of n is equal to minus infinite x of n z power minus n, this term, the definition of the Z transformation. And in the right hand side, z minus 1 x of z minus z into x of 0. Expand this function as 0 is equal, substitute there, x of 1 minus x of 0 z power 0, x of 2 minus x of 1 z power minus 1, x of 3 minus x of 2 z power minus 2, and so on. And you can write this here also. So what is the last term after substituting the infinite? X of infinite plus 1 minus x of infinite. Okay, and z power minus n, z power minus 1 also, minus infinite. This becomes of the 0 actually. So in this, all the z terms is a 1. Limit, apply the limit z tends to 1 on both sides. Z tends to 1 on both sides. If it is a z power minus infinite means definitely it becomes of the 0. But I am substituting the z is equal to 1 here. 1, 1, 1, 1, all the terms. Got it, my dear students? So see, the limit z tends to infinite, z minus 1 x of z minus z tends to 0, z of x of 0, this is the right hand side function, x of 1 minus x of 0, z power 0 is a 1 power 0, x of 2 minus x of 1, z power 1, 1 power 1 is a 1, and so on. Okay, so x of 1 and minus x of 1, and x of 2 for the second term, there is x of minus x of 2 will get. Like that, all the terms is get cancelled, but the last term is x of infinity will get. So x of 0 and x of 0 get cancelled. X of infinite is equal to limit z tends to 1, z minus 1, x1, x of z. Okay, the final value theorem. And these all the conclusion of all the properties we have. The first one is a linearity property. So linearity property saying that a1 x1 of n, a2 is a a2 instead of a2 they are taking the b here. A x1 of n, the b x2 of n, a x1 of z and b x2 of z. And second property is a shifting property. Shifting property. In that shifting, m is the positive values, negative powers of z is multiplied for the unshifted z transformation. And if you can take the second case for positive negative values of m, positive powers of m will get, and it is multiplied with the x of z. Okay. Next one is a scaling property. Scaling in the z domain. A power n x of n is a x of z by a, or we can also write as 1 by a into x of z. The 1 by a is a scaling to the z domain. And this one is a time reversal property. Time reversal property. X of minus n is a x of z inverse. X of z inverse or x of 1 by z. Got it, my dear students? And similarly, the x of k and x1 1 by k, that is a z power k. This will get in the time shift property itself, but here the time shift is in the multiplication factor z power m, but the k will get inside. Why it is inside? The scaling is applied the a power n in the x of n, the amplitude scaling. Here the time scaling is occurs in the z domain. But if I am taking this x of n by k here, you see the n by k to get the z power k value. So no need of this one, you can remember. Next, the differentiation property. Differentiation, that too in the z domain. Differentiation occurs in the z domain. Or multiplying n signal, n into x of n is minus z d by dz of x of z. Differentiation in z domain. And next is seventh property is a conjugate property. Conjugate property. What is a conjugate property? X star of n is x star of z star. Next, eighth property is convolution property. Convolution in time domain. Convolution x1 of n with the star of x2 of n, x1 of z and x2 of z is a product. Time is convolution. Here, frequency domain is a product. And multiplication property. Okay, x1 of n with the x2 of n, using this in the multiplication property to prove, we are using the inverse Z transformation formula. We are using the inverse Z transformation formula, my dear students. It is 1 by 2 pi j the integral x1 of v and x2 of z by v inverse dv. This is a dv, my dear students. And next is a correlation property. Correlation property in the Z transformation. R1, 2 of n is x1 of z and x2 of 1 by z. One is a normal Z transformation, other one is a time reversal Z transformation. Z inverse or x2 of 1 by Z. Okay, and this also no need of this one. Sum of n is equal to minus infinity to n x of k Z by Z minus 1 into x of Z. Forget about this one. And Parseval's theorem. And these also. We didn't cover these two properties. Linearity, shifting, scaling, time reversal, differentiation in Z domain, conjugate and correlation, convolution, multiplication property, correlation property, and the Parseval's theorem. Okay. Parseval's theorem stating that the sum of n is equal to minus infinity x1 of n and x2 star of n. Here also, to prove this Parseval's theorem, you are using the formula for the inverse Z transformation. Is 1 by 2 pi z the integral x1 of z, x2 star of z star minus 1, or x2 star of 1 by z star, z inverse dz. Correct. And initial value theorem and the final value theorem. Initial value theorem saying that limit n tends to 0 x of n is equal to limit z tends to infinite x of z. And final value theorem saying that limit z tends to infinite x of n, not the z, n tends to infinite x of n, limit z tends to 1, not it is a 0, my students. Only you have to remember this one. Limit z tends to 1, z minus 1 x of z. Because it is not the continuous, we are applying for the discrete. So discrete means from minus infinity to 0 means you can take from 1 to, or 0 to infinite means you can take the minus 1 to minus infinite. Got it? It's a brief description of the conclusion of all the properties here. 1, 2, 3, 4, 5, 6, 7, 8, 9. There is no here, this one. And 10, 11, 12 properties. Got it, my students? Then in the tomorrow class, we can see some examples in the Z transformation. Examples in the Z transformation. So any doubt up to these properties? Okay, thank you.